Hello everyone and welcome to this edition of Water Drops. Today we're going to be talking about pond design basics in InfoDrainage. And if this workflow sounds a little familiar to you, that might be because about a year ago we put out a similar workflow video, but that was focused on the interconnectedness of ponds in InfoDrainage. So what we did is we had a series of ponds already set up, we ran an analysis, and then we just looked at the backwater effects because we had those ponds linked up together and because of course we're using that dynamic solver with the swim engine. But today's workflow is going to be a little more in-depth in terms of how to actually build ponds in InfoDrainage. What tools are available to you in InfoDrainage for the sizing and routing of these ponds, as well as what tools are available to you in this tool for designing outlets. So we'll take a look at a few different items there. We'll look at the different outlet types. We'll add a few different outlet connections as well as a multiple outlet type. So something to model essentially a structure that has multiple orifices, or a weir and an orifice, or a weir and a gate. And then we'll also show how to set discharge elevations and requirements so that we are controlling the rate of discharge from our site. And also scattered throughout this workflow video, we'll be using the comparison reports a lot. So there's definitely going to be some phase management aspects, as well as creating those comparison reports to quickly compare between pre and post development, both runoff volumes and discharge rates. And then at the end, as a cherry on top, we'll bring that finished pond to Civil 3D so we can take a look at what that looks like. So here I have a hypothetical project for a residential area. You can tell this is just an illustration that I have loaded in the background that I'm going to be designing on top of, but essentially I have a residential development coming into this open space. I'm obviously going to be putting in a pond down here, and we're going to be discharging to this existing waterway. But what I really want to point out here is some phase management tools before we begin and how these are useful in the sizing of those detention ponds. So typically when you're adding a pond, the purpose is again to store that water, store the runoff, the increased runoff that we see from our site due to the increased imperviousness values, and detain that and slowly release it so that it's not all just draining off the site. We're going to be sizing this pond for a water quality event. So again, all of this just depends on the jurisdiction that you're working in, what those requirements are going to be. Sometimes you have to detain the 100-year event. Sometimes you just need to provide enough storage for that water quality event. Sometimes it's a combination of each and you can get some credit towards that 100-year detention for those water quality simulations. So of course this is all going to depend on your jurisdiction, how much water you are supposed to detain, as well as the runoff rate. So once this is filled up and you start to discharge to your downstream water course, the rate of that discharge is also something that is typically regulated. And a common thing that stormwater authorities will check is that the runoff rate of your new developed site does not increase from the runoff rate that was on your undeveloped site. So over here in the phase management, I have a pre-developed and post-developed phases here. So the only difference between them, and I can toggle between them here, is just that this catchment area is changing. So I have this model just as one large catchment area. I don't have any other, I haven't broken this up. I just have, again, one large catchment area, and the runoff parameters are just changed between the two. So to get a quick idea and kind of a starting point for this pond design, I'm going to generate a quick comparison report between these two phases to look at the increased runoff based on the runoff parameters associated with the more pervious or the more impervious or developed situation here. So I clicked on comparison report. Here you can see which phases I have selected and that I want to compare between. I only have a few storms selected here. So I have a water quality event, just kind of that first 1.2 inches of rainfall. I have a 10-year event and a 100-year event. And then here I can also go into which results I want to show. But today I'm just going to be looking at these runoff values here, specifically the max outflow. So you can see that in that pre-developed phase, I have 35 cubic feet per second draining off the site. But in that post-developed phase, with the runoff parameters I have associated with it, this has increased. So we're going to try to decrease this post-development runoff. And how we're going to do that, we're going to build a pond, store that water, and then slowly release it based on our outlet works. So now let's go ahead and add a pond. And what I'm going to do is I'm going to duplicate my post-development phase, and then we'll make the edits to that duplicated phase. So we'll go duplicate, going to give this a name. You can see that I've worked through this workflow a little bit before. That's why I have all these redundant phases here, but let's call this Basin Design Webinar. And then we can see that this phase is active here, so now that's what I'm seeing. Any changes I make will be to this Basin Design Webinar phase. So now let's add the pond. There's a variety of ways that I could do this. I could, if I do have a pond outline, I can import that from a CAD format, so such as a DWG. Again, it's just going to be looking for like a closed polyline, or if I had a shapefile, I could import it that way. But I am just going to digitize this manually. So how to add a pond manually, over on the toolbox side, go to stormwater controls, and here you can see the pre-packaged templates that InfoDrainage has in it. So there is a pond, and that's what we're going to be doing with today, but take note of just the other templates that you could potentially utilize. To add this, I'm just going to drag and hold and drop this pond into this area here. And then I'm going to digitize the pond, so just draw the outline. Now I'm adding vertices here. The contours that I'm seeing here are from the surface file, and while I can't snap to those contours, if I did have a background CAD image, I could snap to my CAD line work. To turn on the snapping, you go here, select snap, and so then I can import that pond that way, or be more specific with this pond outline. But this rough drawing is going to suffice for now. Let's go into this pond and give it some dimensions. So a few things to note about this window here. Over on the right hand side in this little window, I can see what shape my pond is. You can see that it has been kind of defaulted to this triangular design. I'll show you how we can tweak that. If you already had stage storage data in a tabular format, you could also just copy and paste that here, and then this will update. The exceedance elevation and this depth that has been populated here come from the surface data in the file. So I do have surface data in the file. It's reading that the top of this pond is at 117.8 feet here. The first thing I'm going to do is actually change this so that I can give this a depth. So I'm going to say I'm going to start with this pond being 4 feet deep. By toggling this to base elevation, that allows me to edit the depth here, and then it will tell me what that base elevation is. Alternatively, I could select this, change the base elevation, and then the depth will populate to whatever the difference is between that exceedance and base elevation. The next thing I'm going to do, it did populate the depth here as that exceedance elevation, but that of course doesn't really make sense. I'm just going to enter in 4 feet here because that is the depth. And then I'm also going to copy and paste the area to the bottom of my pond. And so now this will give our pond a nice, just kind of cylindrical shape here. But of course, for safety reasons, we don't want these just pits as ponds. We're going to change the slope, the side slopes of this to give it something a little safer and also just a little more natural. And a quick way to do that is going into the sizing calculator and selecting side slope. So I'm going to give this a side slope of 0.25 feet over feet, or a 4:1 slope here. And I'm going to choose to maintain the top area so that this top area will be the same, but then slopes will be applied in that base area will decrease. Press OK, and we can see those changes made to the shape of our pond here. And so that's how you can give this pond some initial dimensions, an actual shape. And now this pond, if I were to run an analysis, would have storage, and we could actually view those results. I want to also point out that when I drew this pond in here, it automatically linked this subcatchment to there because there's no other elements in the subcatchment, and this pond is entirely within that catchment area. So it automatically connected my catchment area here. If it didn't, and if I wanted to change which catchment area was connected to this pond, that is done by right-clicking on the catchment area and then reconnecting inflow. It's already connected here, so I'm just going to press escape. But that's how you could link the catchment areas to the ponds. So I've gone ahead and made a couple changes here. I did decrease the depth by a foot, so I updated that here and here. I also added freeboard, so I added a foot of freeboard, so now that if the water surface elevation in this pond exceeds this level here, it'll be flagged as a flood risk, even though the pond's not actually overtopping. One other thing I want to point out that you'll need to do before you run an analysis in your pond is in this advanced tab, you do need to add a Manning's value. Now, this Manning value only gets used if we're running a 1D, 2D analysis and the pond overflows, and then that surface data and then the flows are applied to the surface. However, InfoDrainage just requires that if I were to validate this model and try to run a simulation, this wouldn't update. So just a key note, of course, if you try to do this and validate it, it'll take you to where you can add this, but I just figured I'd show this here. Now, again, I could go ahead and run an analysis and view the results of this pond, but something that can drastically reduce the number of iterations you might need to do in your design, as well as kind of move away from a guess and check workflow where we run it, we view the results, and then we change it, and then we go back. So something to get you to a good starting point is this sizing calculator. So I already used this again to establish the side slopes of my pond. So this is where we put in the 1 to 4 foot side slopes here. But I'm going to actually size this based on a water quality event. So some jurisdictions have a first flush requirement where you need to store the first 1 to 2 inches of rainfall that fall onto the site for water quality purposes. So in this runoff reduction volume here, I can choose design up to the exceedance value. So this is going to size the pond and allow for storage up to the top of the pond. But for this example, I'm going to design up to freeboard. So essentially we're only going to have 2 feet of available depth here. And then I can choose to either update the entire areas of my pond or just the depth. And we'll go ahead and update that entire area. So now we'll go into the water quality volume calculator here. I can choose to base this off a runoff reduction or a simple water quality volume. That's what we'll go ahead and use. Input data type, I could manually enter in some parameters of a catchment area that it would use to calculate the volume that this needs to store. However, I already have a catchment area in here with those associated runoff parameters. I have this urban catchment area. So by using plan data, I'm just going to tell the program to use this catchment area that already has a true to site or true to scale area associated with it. And then the next thing here is just to enter in the precipitation depth. So if you can recall from that first comparison report, my water quality event had a 1.2 inch depth. So we're going to go ahead and use that. Now, if I press calculate here, I'll talk through just what we're looking at. So the target volume is what the tool has calculated as how much volume we need based on what we just input. The achieved volume is how much volume our pond currently has. So we're seeing about 9,000 cubic feet of untreated volume, so it's failing. This achieved volume is also shown here. So as you're initially building out this pond and changing the area and the depth curves of that pond, this will automatically update to reflect the actual volume of this pond based on the outline we have here. Again, those areas and volumes that are reported there. However, in this water quality volume calculator, it is reported here. So essentially, this is saying that we need to increase the size of this pond to store those first 1.2 inches of rainfall that are falling on our catchment area. So I'm going to press OK. I'm going to move this off to the side here. I'll press OK here as well. And so by pressing OK here, I'm accepting these changes that we just calculated in that sizing calculator. So you can see the volume has updated to 46,000 from 36,000 or 30-something thousand that we had earlier. Now, if I press apply, you'll see the outline of this pond be bumped up. So now we have a true to site representation of how big that pond needs to be based on a rational method based preliminary sizing of this pond. And so I do want to emphasize that it is a preliminary sizing of the pond. We'll still want to run the full analysis to see backwater effects of if we had other elements, and to use that full swim analysis to see what's going on, as well as to access those comparison reports. However, again, these sizing calculators can drastically decrease the number of iterations that you might need to do. And while we did a sort of water quality volume calculation here, you can see that there's a bunch of different methods. So you could also just generate a quick storage estimate. You can also just quickly scale the pond. So if I wanted to just scale it by a factor of 2 or decrease it by a factor of 0.5, I could do that. And there's other methods in here. And you can read up on these methods by simply pressing this help button, which will take you to our help file. So I've rerun the comparison report and I've turned on the basin design webinar phase. And so now you can see in that max outflow, I have a 0 value for the max outflow and for that total discharge volume. So when you put in a stormwater control, it sort of turns off the ability to allow that runoff to freely exit the site. However, if I go to stormwater controls here and I look at that pond, we can see just a hydrograph quickly about the total inflow and the total outflow. So I do have nothing leaving the pond. You can see this red line here is 0. I can also pull up the stormwater control summary table. I can sort by critical storm here. So we can see that the pond in the 100-year event is flooding. I have negative 803% available. So let's go ahead and add an outlet to this pond now to start discharging some of the volume that's entering this pond. So to add an outlet to this pond, I'll double click on it and we'll go to the Outlets tab. To add an outlet, I'll just press this plus sign here. I can give this outlet a different name. I can designate a connection. I have no connections in this drawing currently, so there's none that I can choose from here. And then I have this outlet type. If I click on this drop down, I can see all the different outlet types available to me. If I want more detail on how InfoDrainage handles these different elements, I can, of course, always just click on this help file and move through those different types and see what kind of inputs they require and so on and so forth. So we're going to go ahead and start with essentially a low flow orifice here. So by designating this orifice, of course, you need a diameter, a coefficient of discharge, and an invert elevation for that orifice. And so rather than hard coding in an orifice here and then running an analysis and viewing those results and seeing if this outflow is going to be big enough, what I'm going to do is actually just calculate the diameter of this. So this diameter calculator, it's available for most different outlet types in terms of calculating how big these should be. And similar to the pond sizing calculator, these are in here to help reduce the number of iterations that you might need to do, and again, sort of move away from that guess and check workflow and provide a more informed first guess. And it's also nice just to have these in here rather than in a separate calculator or a separate spreadsheet. They're just built in, they're at your fingertips, ready for you to use. So if I go ahead and enter in a few parameters here, if you were paying very close attention, you may have seen in the comparison report that my pre-development outflow was about 15 cubic feet per second, lower than my post-development outflow. So again, we want that post-development outflow to match and not exceed that pre-development outflow. So I'll go ahead and click on that. And we can see that this is going to be a rather large pipe here. But again, this is just to kind of sort of get an idea based on these design considerations. I'm actually going to go ahead and just give this, hard code this in and give it a 2 foot, or I'm going to make this even smaller actually. We're going to say that the design depth is 4 feet, design flow is 5 feet, so an 18-inch outflow here. So I'm going to add another outlet here, and I'm going to add a weir. So I'll press add outlet, change this outlet type to weir. And so similar to the orifice, I have the option to add some calculators in here. I can set some parameters. I'll give it a design flow. This is looking like about a 3 foot weir here, so I'm going to just enter in 3 feet. And again, just having those calculations at your fingertips. So having run an analysis, I'm greeted with the stormwater control summary. You can see that I do have some outflow values here now, so I am allowing this flow to exit the pond. If I sort by critical storm again, we can start to see this has obviously gotten better now that we have an outflow value here, but this in the 100-year event is still at risk of flooding. So I might want to go and take another look at those outlet controls or make the pond bigger. Let's go ahead and run another comparison report and see what our discharge rates are looking like. So you can see here, even though that pond is still flooding or at flood risk, the outflow from the pond here is now below those pre-development conditions. So these are just sort of things that you should check in finalizing your design. Again, you're going to want to ensure that you are up to date with your jurisdiction's requirements, but here's where you can start to make those comparisons. Now, another part of outlet design in InfoDrainage is, of course, actually giving those outlets a physical location. So though I've added outlets to this pond, you can't see them anywhere. So if I want to go ahead and place those, if I right click on pond and select specify inlet and outlet locations. And so any inlets or outlets to this pond are now listed here. So I have an inlet coming from the catchment area. I have an outlet representing my orifice and my outlet representing my weir. So let's just go ahead and place this orifice first. When I select on that orifice, what it does is essentially adds this orifice element that I can now move around my pond here. I'm going to do the same thing for that weir. So it adds this sort of physical outlet location, and then I can place that so I know exactly where these elements are going to be in my drainage design, and so that none of this information is lost when I need to actually move this to plan production. Now, the last thing with outlets that I want to demonstrate is how to model a multiple outlet type. And so you might be thinking, well, I have multiple outlets here. What's the difference? The difference is that in the setup that I have here, where I have essentially 2 different outlets, you can see that these are going to different locations. They can be placed in 2 physically separate locations. They could have 2 separate outlet connections. But what if I wanted something like this picture here, where I have a single outlet control structure? It's going to end up going to the same place. However, there's 2 different ways that flow can enter this outlet structure. So I have this orifice here. I actually have 2 different orifices here at different levels. And then I have this opening here, which is going to be modeled with a gate outlet type, because if unsubmerged, this is going to be weir flow, but then when submerged, it's going to act as orifice flow. And again, this is the help file that I'm looking at, so you can essentially click through the different types of outlet controls and view their parameters and read about them in further detail. So again, when unsubmerged, this flow through the gate is calculated using the weir formula. When it's surcharges, it's going to use Torricelli's equation. So we're going to go ahead and model something that looks like this here. So for comparison purposes, I'm going to duplicate this phase again. I'm going to rename this phase to multiple outlet. So you can see how these phases can be used not only to kind of model different conditions, so pre and post conditions, but they can also be used in sort of the optioneering process, and so that you can compare and contrast between different design alternatives. So now in this multiple outlet phase here, we'll go into the pond and add an outlet with that multiple control type. So I'm going to get rid of these two outlets here, add a new one, and we are going to select multiple. So you'll see this invert elevation here. You'll typically want to set this to the bottom of your pond. When you add the different outflows to this single storage structure, everything's going to be based in feet above invert. So keep in mind what your invert elevation is here. I'm going to press edit, and here's where I can start to add the different controls to that single structure. So first we'll add an orifice. I'm going to just give this a 1.5 foot diameter here. Again, I can use that calculator similar to what we just showed. And then here's where I can say depth above invert. If I want it right at that same invert elevation, I'll leave that as 0. And then I'm going to also add a gate. We'll say that this is half a foot high, about 3 feet across. You can add a coefficient of contraction, and this is not going to be right at the invert elevation, of course. Let's say this is about 3 feet above that invert. So that's how you can add these multiple controls. You can add as many of these as you need. There is also this solver here, and what this says is it attempts to calculate the parameters for each individual control that are needed to maintain the corresponding desired design depth and design flow. So selecting this option, it'll validate the desired design flow and depth, but it's not going to validate the individual control parameters. So for example, the height of a gate, so those must be entered correctly beforehand. But I'm not going to use those in this situation here. And I'm just going to press OK. And so you can see this depth outflow curve be populated, and essentially InfoDrainage is just calculating this head discharge rating curve based on those multiple inputs that we set up. I want to also point out this outfall details option. So once you add an outlet, you can edit these outfall details. And what this looks like is, so let's say this downstream water course here, this river that we're discharging to, has a known water surface elevation or has a elevation curve. The water elevation in that pond or in that river changes over time. This is more commonly applicable for tidal situations, but either way, you can set this outfall type from a free discharge. So essentially this free discharge, it's allowing flow to leave the pond no matter what, allow it to leave freely. I can set this to a fixed surcharge elevation or a variable surcharge elevation. So again, that variable surcharge elevation is going to allow you to use an elevation curve. You'll add that elevation curve here. A fixed elevation or a fixed surcharge elevation, you'll just enter in the elevation here. But for now, we're going to go ahead and leave that as a free discharge type. I'll press OK. Go ahead and just place that outlet control just for fun here. So you can see we have this outlet. I'll move it over here, and then we'll run an analysis again. So having run that analysis, let's go ahead and just look at the comparison report again, see how this outlet type is comparing against our other outlet types. We'll select, make sure that this phase is also selected, update preview, and then we can see the max outflow here and those total discharge volumes. The max outflow is really kind of what we're looking at. We can see that multiple outlet is allowing for more flow to leave the system. So if I want to export the information about this pond, I'll go to tables, and then I will, under stormwater controls, I can expand this and select all the information that I want to display about this pond. I can also check the outlets and add or remove information about the different outlet types in here. But then if I expand this table, I can see all of that information in one location, and this can be easily exported to Excel or just printed to a PDF. So the final step in a drainage design process would be, of course, to create construction drawings or detailed plans for your drainage design elements. Here you can see this is a detailed sort of finished design, so I've split up the one giant subcatchment area into multiple. I have it routed into a pipe network, which is then draining down into this pond. I have an overflow weir, I have an outlet type, and of course I want to get this into Civil 3D so I can create those final plans. Now I've already imported this into Civil 3D using this import from InfoDrainage function. I'm not going to step through this. We do have many videos on the integration of InfoDrainage with Civil 3D, but just want to point out what comes over again in terms of the actual pond element itself. So I have, of course, my Civil 3D pipe network, my catchment areas, but as related to the pond, I have this outgoing connection with that orifice. I have the actual footprint of the pond here. So I have the top of pond elevation, I have the bottom of pond elevation, and this is all maintained in its true to site form. So if I go to orbit here, then I can move around and actually see the three-dimensional location and dimensions of this pond. And so that does it for this edition of Water Drops. Again, it's kind of an extended version of Water Drops. I know that was a bit long, but we did cover a lot. We basically started with just how to add a pond, how to give it some initial dimensions. We used the sizing calculators to get an initial idea of how big that pond should be. It's important to remember that this is just an estimation and we still want to run that full analysis, which we also did, and we used the comparison reports to look at the pre, post, and pond phases that we had to look at that discharge rate. And then of course we added some outlet structures to that pond, so we looked at modeling multiple different outlet types. So we had an orifice and a weir going to separate locations, but then we also looked at a multi-stage, multiple outlet type that is going to the same location. We also looked at the calculators there. So all in all, really hopefully what this workflow showed was that you can lay out your ponds, size them, size your outlet connections, quickly compare between different phases and different design alternatives to get a good understanding of how your design is performing, and then of course how you can bring that information back into Civil 3D for final plan production. And that's it for this edition of Water Drops, and we'll see you next time.